All right, everybody, welcome to week 4 and section 14.3, which is motion in space. So we're going to look at position, velocity, speed, and acceleration. We're going to look at it in 2D and in 3D. We've talked about this a little bit, particularly on Monday, thinking about these vector valued functions as a position that an object is in space. And we looked at actually figuring out the speed of an object. We looked at that on example 4 back last Monday on day 5. So you can take a look at that as another example of these kinds of problems. So our definition of position, velocity, speed, and acceleration, they should be really no big surprise. They're similar definitions as what we have for 251. So if we let position of an object moving in three-dimensional space be given by our vector valued function, so again, it outputs a vector of where it is at that time t. So here we really are thinking about t as time. And so we're going to look at t being greater than or equal to 0. So the velocity of our object is going to be the derivative of our position, just like it's always been, and again, it's derivative of each of our components. The speed, we found that with that example 4 from day 5, where we squared each of the components and then took the square root, and it had that Pythagorean identity. So when you're doing this, watch out for cosine squared of t plus sine squared of t. And that can be just plain old t, or it could be like 4t or 5t, as long as they're both the same. What's sitting inside of our cosine and our sine does need to be exactly the same. And as long as it's exactly the same, this is equal to 1. So watch out for that Pythagorean identity, because the square root often does simplify, and you can make any cosine squared plus sine squareds into 1s. So speed is the magnitude of our velocity, and it's a scalar function. And it's going to be positive, so that's going to make sense that velocity is going to be directional. It's going to tell you where you are in space and sort of where you're headed. And then speed's going to tell you how fast you're going. Then acceleration is, again, just what it's always been. It's the derivative of our velocity function and the second derivative of the position. So nothing new there, which is nice. So like I said, we've gotten an example where you started with a position function and we went and got the velocity function. You can take a look at that example 4 from day 5. So I thought we wouldn't do that in the videos, because you do have a video for that. So I thought we'd start with looking at an acceleration function. A of t is cosine of t to sine of t, and this is just in 2 dimensions. Again, sometimes we'll be in 2 dimensions, sometimes we'll be in 3 dimensions. We're given an initial velocity of 2, 1, and an initial position of 1, 2. And we want to find the velocity and the position vector. So the velocity is going to be the integral of our acceleration function. So again, it is going to be the integral of each piece of our function. This one's not too bad. We're going to get what? Sine of t plus, again, some constant. We always have some constant added there. And then minus 2 cosine of t plus some constant. So that plus some constant, we're going to deal with that with this initial velocity. So again, the initial velocity is telling us when we're at time 0, how we're taking off, what our velocity is. And so this is telling us that our output is 2 when time is 0 here, and our output is 1 when time is 0 for the y component. Oops, and then I didn't put 0 in there, did I? That's why erasers are great inventions. Okay, so each of these we just need to solve for our C1 and C2. So sine of 0 is 0. So that first constant is 2. Here, cosine of 0 is 1. So we get that, and we get, adding 2 to both sides, we get 3. So actually, we'll just stay purple here. So our velocity function is going to be sine of t plus 2, and then negative cosine of t plus 3. So there we are with our exact velocity function. Then to get our position function, which we usually call that r, I'm really used to calling it p, so I will try not to write that, but we'll call it r, and that's going to be the integral of our velocity function. So again, it's going to be back up over here, and it's going to be the integral of each piece. So we're going to get negative cosine of t plus 2t, and then plus some constant. And then just so we don't get confused, we'll call the constants here d. Or you call them like C3 and C4. It's totally up to you. You could call them whatever letter you want. We're just going to use a letter so we don't get confused. And then minus 2 sine of t plus 3t plus d2. All right, so now we're going to use, we'll get a different color here, our initial position to figure out what our two constants for our position function are. So again, we've done things similar to this before. So this is again saying when time is 0 for the x component, the output is 1. So if we plug in 0 for both of our times, we get that our output's 1. And same here, our output is 2 for that input of t being 0. So we just need to solve these two little equations. Here we are going to get 2d, because cosine of 0 is going to be 1. That's going to give us a negative 1. That guy's going to be 0. So you're going to add 1 to both sides. And here, that guy's 0 and that guy's 0. So d sub 2 is 2. So our position function is negative cosine of t plus 2t plus 2 for our first component, and negative sine of t plus 3t plus 2 for our second component. So again, things we've done stuff like this before. It's just been with one component, with one equation. We just have to do it now with multiple equations. All right, so let's take a look at this now where we've got a little bit more of a situation kind of wrapped around this. So we've got a golf ball has initial position of r of 0 is 0, 0. So it's starting at 0, 0. So we're hitting it sort of flat off the ground. When it is hit at an angle of 30 degrees with, that's supposed to be an initial speed. It's hard when you make a typo and the thing is still spelled correct, with an initial speed of 150 feet per second. So we want to find the golf ball's initial position function, or just its position function. Again, got to read my notes before I write this. So when does the golf ball hit the ground is another question. So we want to find the position function, and then we want to figure out when it hits the ground. So this one's just going to be in 2D. We partially know that because of the initial position function they give us. But it's a pretty standard setup here. So what it does tell us is it tells us a little bit about our velocity vector at 0. It's telling us at that time 0 that it's hit so that it's got an angle of 30 degrees. That might be a little small there to see. Draw that a little bit bigger here. So again, not necessarily drawn to scale, but there's our velocity vector, and the magnitude of that velocity is going to be that initial speed. And really watch your units on here, because velocity, it's feet per second. Our position, its units are feet. When we're talking about acceleration, that's feet per second squared. So make sure you're paying attention to things like that, your units. So our magnitude, our length here is that 150. And so we've got our golf ball that it's kind of going off like that, and then it's got whatever trajectory that it has. Okay. But it's going to start off with that sort of initial trajectory that we've got with our velocity vector. Okay, so what do we need here? Well, we need things like the initial velocity. They did tell us the initial velocity. The x component of the initial velocity is going to be that magnitude times the cosine of the angle that vector creates, so cosine of 30 degrees. And our y component is going to be our magnitude times sine of that initial angle. And so we're going to get 150 times the square root of 3 over 2, and then 150 times 1/2. So our initial velocity is going to be 75 square root of 3 in the x direction and 75 in the y direction feet per second. So that is our units for that. Well, to start this, to get back to position, we need the velocity function. Well, we don't have that, but we could think about what our acceleration function is. because we do know that. So we don't have any acceleration in the horizontal direction, but we do have some acceleration in the vertical direction, and that's where gravity comes into this. Gravity. And we're actually going to be using in this problem this amount for gravity, the 32 feet per second. So, that's again where you got to watch your units. So that is our force that's pushing down on this. And so it's down at 32 feet per second. And so that's a y direction. And when we're in 3 dimensions, gravity is going to be your z direction because it's going to be pushing down. All right, so this is actually our acceleration function. So we can get the velocity function by, again, taking the integral of this. And so the integral of 0 is just a constant. And then the integral of 32 would be 32t plus, again, another constant. And then this is, again, where that initial velocity comes in, that when we plug in 0 for time, we need to get out these x and y components. So for our first component, there is no t component, so that means that actually that constant we get needs to be equal to our square root of 3 times 75. And our 75 needs to be equal to negative 32 times 0 plus c2. So 75 is our c2. So this gives us our velocity function, 75 times the square root of 3, there we go, is our first component, and then negative 32t plus 75 is our y component. Then to get our position function, again, so position function, that's going to be the integral of our velocity function. So if we take, again, the integral of each piece here, we're going to get 75 times the square root of 3 times t, because that's a constant, so it gets a t. And then we're going to get negative 32 over 2 t squared plus 75. Oh, I did leave something out. Hopefully you noticed this. Let me get my eraser here. I forgot my constant term. That's extremely important. So we've got a constant there, and then, well, negative 32 over 2, that's 16. Negative 16t squared plus 75t plus, again, another constant. And that's, again, where this initial position comes in. And this is really easy to use to find those constants, because this is telling us when we plug in 0 for our time, our output needs to be 0. So that's going to make it really simple. I can show you plugging it in, but if you do a couple of these, you're going to realize, oh yeah, that means that my constant is 0, because we're just dealing with polynomials and linear functions, and so d sub 2 is going to be 0. So our position function is going to be 75 square root of 3t plus negative 16t squared plus 75t. Okay, now I didn't totally leave myself enough room on here to answer our question, when does the golf ball hit the ground? So we're going to have to take our position function and skip to the end here where we've got a blank page and take a look at that. So when it hits the ground, but we'll stand here, we'll do our calculations on another page. When it hits the ground, that's somewhere, over here. And if you think about what's happening with the components, is that what's going to be interesting is that the x component, it's just going to keep getting bigger and further out, as long as we go. But figuring out when it hits the ground, our x component is going to be something, but our y component is going to be 0. So what we need to figure out is, when is this y component, when is that equal to 0? Because that's going to tell us when it's on the ground, because that's our vertical component. And if it's that vertical component's is 0, we're on the ground. So let's skip this question. Oh, will it not add a page for me? No, add a page. Oh no, all right. Maybe it's mad because I'm horizontal here. Well, we'll make some room. We can do this. Which? Because this is not too bad. 75t is equal to 0. So setting that equal to 0, we are going to get, if you factor out a negative t, 16t minus 75 is equal to 0. Set that 16t minus 75 equal to 0, and you will get t is equal to 4.69 seconds. And so that's when it's going to hit the ground, and how far it's going to have gone. That is what we were thinking about there with the x component. That is our x component. That's how long it's gone there in that 4.69 seconds. So we need to take that time that we got and plug that in for our x component, and that'll tell us that horizontal distance about how far it's gone. So this is, I guess this was the answer of our question of when it hits the ground. So that's when it hits the ground. Whoa, when it hits the ground. And this is how far it's gone, which ends up being 100 or 609.24 feet. And I checked that out. That's only about 200 yards, which that does make sense in terms of golf balls. So we're okay there. I always do like to make sure things make sense. Okay, let's take a look at one more of these. And this one's in 3 dimensions. So we got another golf ball, but we've got another component here. We're going to have a wind here. So we've got a golf ball and it's hit east with an initial velocity of v of 0 is 50, 0, 30 miles per second. And then there's a crosswind on this, and the crosswind is blowing north to south, and it produces a southerly acceleration of 0.8 meters per second. So if we're starting here again at 0, 0, so our initial position, we're hitting it off the ground, and we're hitting it east, and this will be north, and this will be east, and this guy will be up. It's going to go something like that because it's getting pushed a little bit off of east from that wind. It's producing that southerly wind, so it's going to push it towards the south. So with this, our gravity that we're going to use, since now we're in meters, we're going to use this 9.8 meters per second. And our acceleration function, so there's still going to be no acceleration to the east, but from the north, we're getting pushed to the south. We're getting pushed in that negative direction. So that's going to be negative 0.8. And then we've got gravity, which is also, that's pushing down. That's a downward force. So it's going to be negative 9.8. So there's our acceleration function. Our velocity function, again, it's the integral of that acceleration function. And whoops, put an extra equals to in there. I was thinking about the next line I had to write. So the integral of 0, that is just a constant. And then each of these are constants. So they each get a t. And then their constant added on there. And then, of course, we have to look at this initial velocity that they gave us. So that first one tells us that c sub 1 is equal to 50. The second one tells us that, again, when time is 0, that initial velocity is 0, so c sub 2 is 0. And then the third one, again, says that when time is 0, c sub 3 has to be equal to 30, so c sub 3 is equal to 30 there. So our overall velocity function is going to be 50 negative 0.8t, there we go, I can speak, negative 9.8t plus 30. So there's our velocity function. And then now to get our position function, again, we take the integral and we get our constant terms divided by 2, t squared plus d2, and then negative 9.8 divided by 2, t squared plus 30t plus d sub 3. All right, I will save us on the constants here. I will let you make sure that I have everything right. But remember, our initial position is 0, 0, 0. So hopefully this is making sense of why all of these constants are 0. So here is our position function. So that's going to tell us where this golf ball is at any given time. So how far does the ball travel horizontally? So again, what we're looking for here is this vector right there. And we're looking for the magnitude of this vector. So we want to know how long is that vector. So wherever it travels, how long is that? So first off, we have to figure out when does it hit the ground. So that's kind of the first question. So hit the ground, question mark. Okay, it's going to hit the ground when that z component is equal to 0. So when it's hitting the xy plane, that's when it's hitting the ground. So that, because that's what the xy plane is, it's the ground. So we need to take, oops, and I lost my, it looks like when I transferred that, I lost a 0 there. So that should be 30. So we can solve this just like we solved the one on the other page. So we get 49t minus 30, 4.9t, sorry, minus 30 is equal to 0. So if you solve that, 4.9t is equal to 0. You get t is equal to 6.12 seconds. You also get t is equal to 0, but that's when you start, so that's kind of boring. And then we want to look at these two components, the x component and the y component. So we want to look at that 6.12 plugged in for all of our variables here, and we are going to get 306 when we plug it into the first component. We'll get negative 14.98 when we plug it into the second component, and we should get 0 when we plug it into the third component. So that is this spot here. I'm going to make this a really big dot. That's that spot there when it hits the ground, when it hits the xy plane. And we need the magnitude of this value of t. So that's going to be the square root of 306 squared plus negative 14.98 squared plus 0 squared. And we are going to get from that 306.4 meters.